All right, let's dive into a really fascinating puzzle that sits at the very heart of, well, trust in our digital world. It's called Byzantine fault tolerance. And it all boils down to one fundamental question. How do you build a reliable system when you know some of its parts might be unreliable, or even trying to tear it all down?
I mean, really think about it. Imagine you and a group of people have to make a huge all or nothing decision. But here's the thing, you can't trust everyone in the room. Some of them might be actively trying to sabotage the whole thing. So how do you make sure the honest folks can still come to the right, unified decision? That's the challenge we're going to unpack today. To really get our heads around this, we have to go back to a classic thought experiment in computer science. It's called the Byzantine generals problem. And honestly, it's the perfect story for understanding the challenges that massive, distributed systems, like blockchains, face every single day. So picture this. You've got these different divisions of an army surrounding an enemy city. Each one has a general. Now they all have to agree on one single plan. The problem is, their only way to communicate is by sending messengers back and forth. And to make things worse, some of these generals might be traitors, actively trying to make the loyal generals fail.
The rules of the game here are super simple, but the stakes, incredibly high. The choice is black and white. Everybody attacks together, or everybody retreats together. If they split up, it's a total disaster. A traitor could just send an attack message to one general and a retreat message to another, and chaos. The entire goal is to design a communication system where all the loyal generals agree, no matter what lies the traitors are spinning. For a long time, this was just a cool theoretical problem. But as computer networks started getting bigger and more complex, we needed a real-world solution. And that led to the first huge breakthrough, practical Byzantine fault tolerance. You'll hear it called PBFT. Way back in 1999, two researchers at MIT, Barbara Liskov and Miguel Castro, published the paper on PBFT, and this was a massive deal. It took the Byzantine generals problem out of the textbook and gave us the first real working algorithm for building systems that could actually tolerate these kinds of failures. So how does this thing even work? Well, PBFT uses this really careful three-step process. First, you have a leader who proposes a plan, like let's attack. Then comes the prepare phase, where all the other generals basically shout to each other, hey, I heard the leader say attack. What did you hear? This is so important because it fleshes out a lying leader. Finally, once everybody confirms that they've heard a solid majority agree on the same plan, they all commit to it, locked in. And this brings us to the magic formula behind PBFT. The system can handle F number of traitors, but only if the total number of generals is at least 3F plus 1. So to handle just one traitor, you need 4 generals total. Why? Well, you need enough loyal generals to form a clear majority that can outvote the traitor and anyone they might have tricked with their lies. Honestly, PBFT was a game changer. It became the foundation for so many reliable systems. But it had one big weakness, a bottleneck that really limited just how big a system using it could get. And that bottleneck has this nerdy name, quadratic communication cost. But what it means is simple. As you add more generals, the number of messages they all have to send to each other doesn't just go up, it explodes. It's like every single general has to talk to every other general multiple times. It gets slow and clunky fast. So for about 20 years, PBFT was the king. But with the rise of things like blockchain, the world desperately needed faster, bigger, more scalable systems. And that pushed researchers to find a better way. Enter hot stuff. I mean, just look at this timeline. It really puts things in perspective. A full 2 decades separates these two breakthroughs. Just think about the leap in technology from 1999 to 2019 in general. That's kind of the scale of the performance jump we're talking about here.
So, what's the secret sauce in hot stuff? Well, for one, it fixes that communication explosion. It's linear, which means it scales way, way better. It also uses a couple of really clever tricks. It uses these things called quorum certificates, which are kind of like a digitally signed petition proving a decision was made. Then it chains these petitions together, creating this super fast assembly line, or pipeline, that makes decisions final much more quickly.
Okay, so let's put these two side by side. It's here you can really see the evolution in action. And this table just spells it all out, doesn't it? That communication jump from quadratic to linear, that's the difference between a system that crawls to a halt and one that can actually scale to a massive size. Hot Stuff also has this really slick, built-in way to swap out the leader if they go offline or turn out to be a traitor. In PBFT, that's a much clunkier process. And that pipeline, that's all about speed. Getting to that final, irreversible decision way, way faster. Look, I know this can all sound like really abstract computer science, but the ideas we've just gone over, they are the absolute bedrock of some of the most important tech being built right now. This is not just a thought experiment anymore.
This quote really just says it all. Any system where you need a group of computers to agree on a single version of the truth, without some central boss like a bank telling them what's what, it relies on these algorithms to keep from falling into total chaos.
And you can see this stuff in the wild, everywhere. Hyperledger, which is a big deal in the enterprise world, uses a system based on good old PBFT. But look at the new wave of blockchains. Meta's Project Deem, major players like Aptos, Sui, and Flow, they all looked at the options and chose to build on Hot Stuff or something very similar because they needed that performance and scale.
So we end up right back where we started, with this question of trust. The Byzantine general's problem showed us just how incredibly fragile agreement can be. But algorithms like PBFT, and especially Hot Stuff, show us how we can literally engineer trust into our digital world with math. It really makes you wonder, as more and more of our lives are built on this distributed code, what's the real value of these guarantees? What's the ultimate price of trust?